Hello, my name is Farah, and my colleague Ghaliah and I will be presenting this project about designing a kinetic facade for an office building in Lebanon. This presentation starts with an introduction, followed by site and climate analysis, project design with a base case, an efficient case, an optimized case utilizing a kinetic facade system, and finally the design builder simulation and analysis comparison. Nowadays, using windows and expansive external glazing as the main components of the building envelope has become very widespread. However, with more transparency comes excessive radiation, heat, and glare, which not only results in higher energy consumptions, but have also been affecting the user experience and interaction within the space. As a result of the previous problems, new techniques and approaches have been established to adapt to our evolving needs, one of which is the kinetic facade system. The geographical location of the project is set in Lebanon, within Beirut and specifically in Al Khudr neighborhood. The entire plot area is 5,768 square meters with 3 surrounding streets and the potential for front and back car parking. The surrounding site characteristics are very geometric, with the prevailing winds from the southeast. The climate analysis focused on the illumination range, radiation range, and the summer and winter sun shading charts. As seen in the massing diagram, the building is composed of 3 volumes, a left block, a right block, and a central atrium. The 2 side blocks consist of 3 floors, ground plus 2, whereas the atrium is completely open with 2 bridges connecting the 2 side blocks. This is the proposed site planning with 2 vehicular access points and parking, both of which can easily lead the people into the building through the central atrium. This is the ground floor zoning plan on the left and furniture plan on the right. The main entrances are through the atrium into a reception and public lounge, followed by vertical circulation. Branching to the left and right sides are typical planning layouts starting with a staff lounge, a pantry, open staff workstations, closed private offices, a meeting room, and finally the washrooms. The first floor is identical to the ground with an added bridge and void over the reception. The second floor is identical to the first floor. And these are the building elevations.
This is the 3D model of the base case from the southwest view. And this is the 3D model from the front. These are the axonometric views by block. Note that the left and right blocks have typical layouts on all floors. The base case wall is composed of 4 layers with a U value of 2.1. The roof is 5 layers with a U value of 0.57. The glazing is a single layer with a U value of 5.9. An annual simulation was conducted to compare and choose the 3 peak months. And so the chosen months are July as the summer scenario, January as the winter scenario, and April as the spring scenario. And these 3 months will be used throughout the 3 cases with a specific focus on 9 a.m. facing east, 1 p.m. facing south, and 5 p.m. facing west. Specific focus was placed on the solar gain, fuel totals for cooling and heating, as well as the CO2 production. And this is the summary for the base case. The higher the solar heat gain, the more the cooling electricity consumption, which increases the CO2 production, as in the case of July and slightly in April. The heating gas in January is higher in the morning and evening due to the lack of insulation and the need to warm the space. The sun path diagram was used to assess the angles of incidence and shading requirements to be added in the following cases. The daylight factor and illuminance values were not aligning with the standards in the base case, and so an improvement is considered in the next case. A CFD analysis was also carried out for the base case to analyze the airflow, velocity, and pressure outcomes to be improved.
The efficient case relies on the IRIS Green Building Rating System, which is the official sustainability rating system in Lebanon provided by the Lebanon Green Building Council, in addition to the utilization of the Lebanese Center for Energy Conservation. This figure illustrates the ASHRAE design guidelines which are in compliance with the ERS rating system and are implemented in the project. In compliance with the ERS rating system, the efficient case uses a low E double glazing with 20 mm argon gas and a U value of 1.5 and a solar heat gain coefficient of 0.15, and triple glazing for the atrium with 20 mm argon gas and a U value of 0.7. A heat reflective paint with a high solar reflectivity is added for the roof, and stack ventilation to achieve passive cooling during the summer. The efficient case wall is composed of 6 layers with a U value of 0.33, while the roof is 7 layers with a U value of 0.26. This aims to reduce the solar gain and reduce fuel consumptions and CO2 productions. This is the 3D model of the efficient case implementing horizontal louvers on the atrium roof and south facade to reduce solar gain and cooling electricity in July and April. This will also help reduce intensity of daylight factor and illuminance values while still allowing the low winter sun to penetrate the space for passive heating. And this is the front view facing south. This is the 3D model interior of the efficient case atrium utilizing louvers as a shading mechanism and openings throughout for natural ventilation. The efficient case simulation results show a decrease by more than 50% for the solar gains, fuel totals, and CO2 production with an improved ventilation due to the stack ventilation. The fuel breakdown results for cooling and heating show more than 50% reduction from the base case results, as well as the CO2 production results have decreased by more than half. To sum up the efficient case, the results show reductions by more than 50% in solar gain, cooling electricity, heating electricity, and CO2 production, aligning with the ERS Green Building Rating System requirements. The sun path diagram in July 15 shows an improvement in the atrium during the summer with the added shading louvers. The efficient case CFD analysis shows improved velocity and temperature values.
The kinetic facade design for the project implements a biomimetic approach inspired by the DNA bases, which are the elements in between the two side strands. The kinetic facade is designed based on 14 rectangular pieces that rotate surrounding a central pivotal point to respond to the varying solar changes during the day. Each rectangular piece can rotate 360 autonomously without affecting the rest of the rectangular pieces, thus reducing the direct sunlight penetration in July and April when needed. However, during the winter, direct sunlight penetration is needed to achieve passive solar heating, and so the kinetic facade responds to this information by staying rotated at exactly 90 degrees, allowing the low winter sun to penetrate into space. Despite the rectangular shape of the kinetic facade, the singular rotation of each element provides interesting forms to the building exterior and interior, resembling that of a DNA helix. The structure is made of stainless steel, while the rotating elements are PTFE, coated glass fiber mesh which diffuses the sunlight before entering the space without completely blocking the view. This 3D view shows the closed facade, intermediate position of facade, and open facade. This is the front view of the building with the closed facade. Facade is in motion until it completely opens. In the optimized case, the kinetic facade has been added on the east, south, and west facing facades and closes according to the sun exposure. This is mainly required during the summer month.
For the renewable energy source, PV panels are utilized with a passive dual-axis solar tracker. Generally, the optimized case analysis shows improvements starting 5% onwards between all 3 months for the solar gains, cooling and heating electricity, as well as the CO2 production. The fuel breakdown results show 5% reduction from the efficient case results. as well as the CO2 production results have decreased by 5%. The daylight factor and illuminance values have also improved with the implementation of the kinetic facade, which has allowed for a diffused light within the space, reaching the 2 to 5% daylight factor and 300 to 500 lux luminous intensity. To summarize the optimized case, there were further reductions by 5% in solar gain, cooling electricity, and CO2 production in July and April due to the kinetic facade. However, the January results remain the same as the efficient case. These are the energy consumptions for the whole building before and after the implementation of PV panels. July saw a 5% reduction in the energy consumption and April a 15% reduction, whereas January was almost the same. A CFD analysis was run using only natural ventilation. The results show the prevailing southwest winds entering through the building and circulating exiting from the opposite side, while also reducing temperature and pressure. A natural ventilation simulation was run for July 15 in order to assess the possibility of natural ventilation while switching off the HVAC system. The July 15 ventilation results show that the mechanical ventilation provides lower air changes per hour and higher CO2 consumptions, whereas the natural ventilation simulation increased the air changes per hour by 50 to 65%, which falls within the acceptable range, and reducing the CO2 productions by 76 to 81%. The July 15 natural ventilation results show a reduction by 86 to 87% for the site energy and a reduction by 67 to 68% in source energy.
To compare the three cases in terms of building materials, the base case has walls with a U value of 2.1, while the efficient and optimized used 0.33. The base cases use a roof with 0.57, while the efficient and optimized use 0.26. For the external glazing, the base case used single glazing with a U value of 5.9, while the efficient and optimized cases use double glazing with U value 1.5 and triple glazing 0.7. In terms of shading devices, the base case has none. The efficient has horizontal atrium louvers on the roof and south facade, while the optimized case implements a kinetic facade. In addition, the optimized case is the only one using PV panels as a renewable source of energy. In terms of annual site and source energy, consumptions have went down from the base case to efficient case by 52% and additional 3% in the optimized case. For the site and source energy by seasonal case, energy consumptions went down from the base case to efficient case by 52% and additional 3% in the optimized case as represented. The solar gains comparison for July 15 shows a 59 to 73% reduction from base case to efficient case and 5 to 12% reduction in optimized case. The solar gains comparison for January 15 shows a 64 to 67% reduction from base case to efficient case, then constant in optimized case. The solar gains comparison for April 15 shows a 61 to 70% reduction from base case to efficient case and constant in optimized case. July doesn't require heating as it is a summer month. The heat and electricity comparison for January 15 shows more than 50% reduction from base case to efficient case than constant result for optimized case. The heat and electricity comparison for April 15 shows more than 44% reduction from base case to efficient case and 52% reduction in optimized case. The cooling electricity comparison for July 15 shows a 50% reduction from base case to efficient case and 5% reduction for optimized case. January doesn't require cooling electricity as it is a winter month. The cooling electricity comparison for April 15 shows 100% reduction from base case to efficient case, then constant in optimized case. The CO2 production comparison for July 15 shows above 50% reduction from base case to efficient case and 5% reduction in optimized case. The CO2 production comparison for January 15 shows from 9 to 10% reduction from base case to efficient case and is constant in optimized case. The CO2 production comparison for April 15 shows a 69 to 82% reduction from base case to efficient case and from 2 to 20% reduction in optimized case.
In conclusion, the building energy consumption for this project has improved gradually through the 3 cases and scenarios, optimizing the performance and aligning with the ERS Green Building Rating System. The implementation of the kinetic facade along with the renewable energy source was a key element, along with careful material consideration and passive heating as well as cooling through natural ventilation in the summer. Thank you for listening to our presentation.